Great. Good afternoon, everyone. Thank you so much for coming. My name is Felix Candelario. I'm a principal solutions architect. My colleague and I, Harsha Sharma, we spent maybe the greater part of the last 12 months talking to customers about how to incorporate machine learning into their workflows that support highly regulated workloads. During those course of conversations, we talked a bit about what the requirements are, and what started to become apparent to us was that there was a need to govern the workflow a little bit different because of their incorporation of machine learning. Now, those conversations that we had, they weren't around what techniques to use or what frameworks to use or what libraries to use. Those conversations were around how is it that one incorporates a machine learning workflow into a workload while meeting all of your requirements, especially when it comes to things like evidence and for compliance. So my colleague and I, what we've done is we've thought that some of the solutions that came out of our conversations would be useful for everyone. So you yourselves, maybe you have workloads that have external regulatory pressures that require a significant rigor. Maybe you have a workload that has significant internal compliance regime that requires that rigor. Or maybe you just want to manage your experimentation a bit better. What I hope to do in the time that we have together is to leave you with a solution that you can incorporate in whole or in part that's going to help you meet some of that rigor that you would need in order to support your workload. So in order to accomplish that goal, I've come together with this agenda. And what I'd like to do is first kind of establish the need for governing a machine learning workflow. Now, it's likely that some of you in this room may already have that need in your head. We're just going to make sure to go over it so that everyone's on the same page. Then we'll actually talk about a typical machine learning workflow. And this will help really illuminate the problem that we're going to try to solve here. We'll go over the solution, and then I'll demo it for you. And then we'll actually do a sample audit so that you understand how this solution actually supports those goals. And then finally, we'll just wrap up with some remarks. And I think this will be a really good use of our time together. So we start at kind of the need for governing machine learning workflows. One workload in particular that is a very good one to help kind of illuminate the reasons for governing a machine learning workflow is a workload that participates in the credit lifecycle decisioning process. This is the process by which a firm decides to extend credit to an individual or an organization. Now, the United States government and several governments across the world, they want to make certain that their citizens have fair and equal access to credit, which is why these workloads are highly, highly regulated. The workload in particular that we'll look at is one that's specific to marketplace lenders. Now, you yourselves may have used marketplace lenders. They have pretty interesting properties that kind of help illuminate the problem even further. So let's talk a little bit about what those properties are. Marketplace lenders are kind of very agile. They are generally smaller organizations than most financial firms. And in keeping with that ethos, they operate almost exclusively online. So if you've used a marketplace lender, you may have only interacted with them via an app or a website. When you talk to them and they talk about why they're very good at what they do, what they'll say is that in part that's because they have a very niche product focus. So they'll only work in one or two products. These products are things like unsecured personal loans, they're real estate-backed loans, they're educational loans, they're small business loans, loans that in some way carry a bit more risk than a more typical loan. And they'll say in part that the reasons that they are able to manage that risk so well is because they're so focused. The other reason is because they use non-traditional data sources in combination with machine learning techniques. Now, maybe you've applied to a loan recently, or you can remember having done so. The kind of data that you would expect to give, that's generally what would be referred to as traditional data sources, or traditional data. These would be things like your name, your address, maybe your income, maybe your FICO score, for example. That's typically thought of as traditional data, or a traditional data source. Non-traditional data sources are things like your email address, or the addresses that you may have had over the couple of years before you've applied for these products. This actually reminds me of an article I read in Wired a couple of months ago, and it was about an emerging body of work from academia where we're taking machine learning models, looking at these non-traditional data sources, and finding pretty interesting correlations. For example, one that was highlighted was that there seems to be some correlation between the likelihood of you paying back a loan and whether or not your email is from Gmail or Yahoo. Or the likelihood of you paying back a loan, whether you have an iOS device versus an Android device. So there was all of these kind of interesting things that are starting to come up in research, and part of those things are things that marketplace lenders take advantage of to help manage their risk a little bit more. So as you can imagine, with that kind of data and this kind of use of non-traditional data sources, there are some different risks that are introduced. And these risks are, for example, things of like potentially greater exposure to bias, right? And that's in part because these are new techniques, these are new data sources. We do not yet know if these are proxies for something else, something that wouldn't traditionally come up. A risk that firms like these can find themselves is that reproducibility is hard. Anyone that's ever done any work with machine learning models understands that being able to describe exactly why the model made the inference that it did, that can be a bit difficult to do. And then, of course, the field itself is in great flux. And what that means is libraries and frameworks are being introduced and being changed, and that requires you tracking all of that information as you, say, try to recreate models. So there are several risks here, technological risk, business risk, credit risk, that become apparent as you start to look at workloads like this. And what will happen is that you'll start to try to implement control objectives to mitigate those risks. So when I talk to my customers around workloads that have these kind of properties, they'll talk about wanting to govern their workflow such that they can provide, on the one hand, maximum flexibility to their machine learning professionals, while on the other hand, maintaining flexibility. They'll talk about wanting the same inputs to result in the same output over and over again. And this is especially important when you're supporting a workload like this. And then also being able to significantly increase the amount of auditability that you have from your workflow in order to meet these kind of requirements. So with those control objectives in mind and this risk and this workload in mind, this should give you a good idea of why there are folks out there that really want to govern their machine learning workflow, because they're going to have to answer significantly important questions. Now, maybe you yourselves don't have workloads that are externally regulated. Maybe you have workloads that are internally regulated because of some compliance regime. Or maybe you just want to manage your experimentation process a bit better. But this should give us all a good idea of why we need to govern these workflows. So what I want to share now, because this is really going to illuminate the problem that we're up against, is a typical machine learning workflow. Typically, when I show customers this, I find that a couple of them blush. We're all friends here, don't worry. And I'm going to walk you through this, and we're going to understand what it is that we're kind of up against as we work through why it is that we came up with the solution that we did. So we start on a Monday. Anne comes into the office after having spent the weekend reading some academic papers, and she wants to try out a couple of techniques that she read. So she sits down at her desk, she has her data set on her network drive, and she's got a shiny GPU cluster out in the corner somewhere. And what she does before she gets going is she looks at a previous project, and she takes this previous project and she kind of hollows it out and makes a new version, right? Something to start from. So she has version 1 of her source code of her model, and she has her data set, and she submits it to the GPU cluster. And out of that cluster, you've got your training job. So at this point now, we have our running training job, and we've got our source code. So pretty easy to keep track of, not too many variables here. And being as productive as she is, she says, okay, well, I'm gonna try this second technique that I read about during the weekend. And she makes version 2, and she submits that to the GPU cluster, and now we've got 2 jobs. So not too difficult, right? I've got one version here, and I've got the training job associated with it. I've got another version here, and the training job associated with that. As that second training job is running, it produces these model weights, and she's going to grab those model weights and she's going to persist them to her network drive. It just so happens that that first training job, for some reason, it failed. It may have hit a bug. And what she does is that she starts debugging locally, and she makes a minor change to version 1, and now she's at version 1.1 of her code. Okay, it's getting a little bit more complicated here. And what she does is she takes her model weights, takes version 1.1, and submits that to the GPU cluster. And now we've got 3 training jobs, and now everyone's confused. So if you're looking at this, I think I've seen a couple people shift down a little bit lower in their seats, just like a ½ inch. This may be familiar. This may be the way things look like for you, which may be fine, right? Maybe you're just experimenting. But this becomes especially difficult when you've got workloads that are depending on this workflow that have a significant need for rigor. Now, as you can imagine, this thing here is pretty error-prone. And it's error-prone because there's a lot of manual orchestration. Now, humans are good at a lot of things. They're good at telling bad jokes. What they're very bad at, though, is doing the same thing over and over and over again exactly as they did last time. So that's going to lead to trouble for everyone involved in this particular workflow, especially if the workload itself is highly regulated. The inputs that she's using aren't versioned. Now, you saw her create new versions. Anyone here that's done any form of development, even very small and insignificant, knows if it's not going in source code repository, it really isn't versioned. Her data set, which she doesn't know, is that her colleague Carlos showed up on the weekend and accidentally deleted a file from the network drive that she was using as her data set. So her data set isn't versioned, and that's going to become very difficult. And then, of course, her outputs themselves, those aren't versioned. So when she puts the model weights into the network drive, who knows what version of code that is. Now, as you can imagine, if a colleague of yours came to you with this workflow and said, hey, what was the version of the model that produced this inference? It's going to be pretty difficult to answer that question. Now, it's with this workflow in mind that myself and my colleagues sat down and said, what's a good solution for this? Now, my colleague and I, we're from AWS. We are kind of steeped in ideas around reducing the amount of friction that's associated with moving code from source control into production as easily as possible, right, and reducing that friction. And what we recognized almost immediately is that this is a problem that's been largely solved by the industry. This is ultimately a versioning problem. This is a problem that we've solved as we've developed source code over the years. And in part, what's happening here is that it's the presence of the data sets, it's the presence of these libraries that is making it difficult for customers to recognize that we just have to treat this stuff like code. And that's what immediately grounded us in a solution that was steeped in CI/CD techniques. So what I have here on the screen is a collection of the services that we're going to use to build this solution. These solutions are in part around CI/CD and the movement of software from source code to actual deployment. Some of these services are around storage and versioning. And one of these services is actually around machine learning. And I'm going to introduce these services as we walk through the solution. So when we interact with this solution, we have an input and an output. Our inputs and outputs here are S3 buckets. S3 is our globally available object store. And what we do here is we place our data sets into that input bucket, and any outputs from our models are going to be placed into that output bucket. These two buckets have been configured with versioning, which means when you put an object into S3, you can immediately query S3 and ask it, what is the version ID of this particular object? If you were to say, take the same file and upload it, and it's the same object, you would get a different version ID. So this is a great way of kind of managing data sets. The next input here is a repo, and that repo lives on AWS Code Commit, which is our Git-like managed service. So if you've used GitHub, if you've used Git commands, you'll know how to use it immediately. And that's where we're going to persist our source. And our source, that's our models, and some auxiliary files that help to define how this particular solution works. So what these machine learning professionals are going to do when they interact with this solution is they're going to upload their data, and then they're going to clone the repo, and they're going to put their models into that repo. And as they make changes, they'll commit, and this solution will run. So when the machine learning professional commits their model into these repos and pushes it up into Code Commit, that's going to wake up AWS Code Pipeline. Code Pipeline is our managed CI/CD service. And what I've done is I've configured Code Pipeline here to run what we call 3 stages. And you can think of these as steps. So when Code Pipeline here is woken up, it's going to start the first stage. And that first stage is called the source stage. And what happens here is that it takes the contents of that repo that it was just committed to, and it puts it into an S3 bucket. And that means that in the S3 bucket, the contents of that repo is now there. This bucket is only available to the rest of the pipeline. And that's the only thing that the first stage does. At the conclusion of that stage, Code Pipeline will then start the second stage. This stage is called the build stage. And what happens in this stage is our service, AWS Code Build, this is our managed build service. What this service allows you to do is it allows you to actually build your software, right? So if you have Java application, it will compile, and then it will ship out that artifact. And what's nice about this service is that that build environment that it spins up for you, it will spin down, and then you only pay for what you use. What happens in this stage is Code Pipeline wakes up Code Build, and Code Build looks for its instructions in the root of that source code directory that was persisted to that S3 bucket. Based on those instructions, what it's going to do is it's going to create a Docker container, and that Docker container is going to have copied into it the contents of the repo, and then it's going to have 3 tags placed onto it. The latest, the commit ID that caused the solution to run, and the name of the repo. And now what we have here is a container that's been pushed into Amazon ECR. This is our Elastic Container Registry service where you can durably store your container images. And this container now has all this metadata information that allows you to point back to the commit so that you could answer with no doubt what version of the model is in that container and who made those changes and when those changes were made. So that'll be the end of that stage. At that point, Code Pipeline calls the final stage, the train stage. It's in this stage that Code Pipeline goes and wakes up a Lambda function. Lambda function lives within AWS Lambda. AWS Lambda is our event-driven compute service. And what you can do with Lambda is you can upload arbitrary code that can then be run in response to a configured event. So you could write a Java method or a Python function and have that woken up. What this Lambda function does is it's responsible for making an API call into SageMaker to create a training job. And it's going to do that based on information that's in a file in that S3 bucket that was made available to the entirety of the pipeline. This Lambda function is going to point to the previously created Docker container, and it's going to point to the input data sets, and that's going to result in a SageMaker training job. SageMaker is our managed machine learning platform. It allows you to collaborate through the use of managed Jupyter notebooks. It allows you to use highly optimized machine learning models that we ourselves provide. And it also allows you to train and deploy your own models, which is the functionality that we'll be using here. That training job is tagged by the Lambda function, not just with the commit ID, but also with the version IDs of the inputs in that S3 bucket. So now we have yet another artifact that refers back to its ancestors and now can answer definitively things like, what was the actual data that was exposed to this model when it was training? At the conclusion of that training job, SageMaker is going to take the outputs and it's going to push it into that output S3 bucket. And that is also versioned. So now you have these outputs versioned, you have these inputs versioned, and of course you have your source code versioned. So that's kind of the entirety of the solution, right? You have the inputs into which you work in and your outputs, and it's pretty well defined. So the properties of this solution, you can probably already kind of start to guess, is that first, it's highly flexible. You may have noticed that I didn't say that the model had to be a TensorFlow model or an MXNet model. I really just said model. It can be anything. This solution will support it right out of the box. Also, the machine learning professional has complete control of the runtime environment, and that's through a Dockerfile that I'll show you in just a bit. This solution is collaborative, right? It's all based on Git, so multiple developers can work on this at the same time. And then this is also repeatable, and that's because we have Code Pipeline doing all of the orchestration between all of the services. This solution is auditable, and that's for two big reasons. The first is because I've gone through great pains of making certain that all of those artifacts are linked to each other so that it becomes easy to pull on a thread and get all of that information. The second reason is that these are all AWS services running on AWS, which means they all live behind an API that you can interact with programmatically. So you could send an API call and tell SageMaker, tell me about this training job. And that makes it very easy to audit. And then finally, although not explicitly called out, this solution is really secure. And that's because any place that data is at rest, we're encrypting it with our key management service. Any place where data is in motion, we're encrypting it in transit. And any place where these services are doing something on your behalf, for example, this Lambda function calling SageMaker or reading from that S3 bucket, we've taken great pains to make sure that we have the least amount of permissions attached to any of these services, which means that Lambda function, it can't delete and it can't write to the bucket. All it can do is read, and it can only read that particular bucket. So there's a lot of properties here that make this especially useful. So now that I've shown you this solution, let's walk through a demo. And what I'm going to do is I'm going to ask everyone here to kind of participate in some make-believe. Let's just make pretend that since the age of 4, I've wanted to be a marketplace lender, and I also happen to be a machine learning guru, and I also happen to be great at AWS. So keep this in mind as we kind of move through this demo, because we're going to need it when we go to the sample audit as well. Okay, so we're back at our solution, and we're going to instantiate this solution. And what we've done here is we've made this solution a template. It's just a CloudFormation template, which means you can run it over and over and over again, and you will get the exact same solution. So you can run it on a per project basis. So I'm going to make pretend here that I have a project that I want to work on, and I'm going to instantiate it. And what I did is I wrote a little utility, a small little command line thing that takes inputs, and it calls CloudFormation. So I'm here at my desktop, and I have a neat little utility that I created called ML Workflow. And what I've done here is I've said, hey, create a project for me and say something pithy about its description. And in the background, it's running this CloudFormation template to start this solution. Now, I didn't want you guys waiting here for 9 minutes for the outputs to spit out, so I just fast-forwarded it a little bit. And what you see here are the 3 pieces of information that I need to be able to use this solution. So I have here my Git URL. This is the repo that was created for me, and this is where I'm going to commit my model and all of my auxiliary files. And then here I have my 2 S3 buckets that have been configured with versioning, one for input and one for output. What I'm going to do now is I'm going to use the AWS CLI, and I'm going to copy my data set into that input bucket. So I'm going to take my data set and my training and testing data set. I'm going to upload both of those. And once I do that, I have now in S3 objects that themselves have versions IDs. And if I were to upload these same objects again, I would get a different version with a different version ID. What I'm going to do now is I'm going to clone that repo locally. When I clone that repo locally, inside of it there's going to be a zip file, and that's just where I keep the standard files that are required to make this solution run, so that I, as the pretend machine learning professional here, can edit it and define things like my runtime. So I'm going to unzip this baseline.zip file. It's going to push out a couple of files. And now what I'm going to do, now that I have this local copy of the repo, I'm going to copy my model, which in this case I've called train. And I'll tell you why in a moment. So in my local repo now on my desktop, I have all of these files, and I'll walk you through each of them. But for the moment, let me just show you my model. This model here, it happens to be a TensorFlow model. What it does is it predicts whether or not someone makes more or less than $50,000 US based on some demographics, and it was trained on the 1994 US Census. This is a demo model. It's one that I understand quite well, and that's why I've used it here. But again, this solution's flexible. This could have been anything. So I have there my training model, and now I have my repo that has some changes, and I'm going to actually push this and commit it into AWS Code Commit. Now remember, that's going to be the trigger that starts the solution running. That's going to cause AWS Code Pipeline to wake up and start our first stage. So that's been pushed successfully. And now let's talk about what's in that repo. So we've got a couple files in there. The first file of import in that repo is the build-spec.yaml file. This file is what governs how code build behaves. So when I wrote this file, I wrote 3 phases, a pre-build, a build, and a post-build phase. And what I'm telling code build to do in this particular file is to log into ECR, get credentials, to construct a Docker container image based on the Dockerfile that is in the repo, and then to copy the contents of the repo into that Docker container, to tag that Docker container with those 3 pieces of information, the latest tag, the commit ID, and the name of the repo, and then to push that into our ECR service. I've configured code build to look for that file in the root of the source code directory, which, as you'll remember, was copied to that S3 bucket that's only available to the pipeline. The next file is a Dockerfile. This Dockerfile is very simple. All I'm doing here is referring to the TensorFlow container image, and I just have it install a small number of libraries. But this here is what allows the machine learning professional to control their runtime. So if they had libraries that they needed to install in order to be able to run this model, that's the place that they would do it. And that's how they can be assured that they're getting the exact same environment every time, and they have complete freedom to edit that file. The next is a manifest file. This is the file where I do things like configure my hyperparameters. It's also where I define what EC2 instance type to use for training when SageMaker starts training my model, which is within this container. It's the Lambda function that consumes this file in order to be able to properly construct the API call that goes into SageMaker. And then finally, you have my actual model itself. Now, when the SageMaker service starts to train your model that's stored in a container, what it does is it uses an entry point called train. And what most customers do is they will create a script that's called train, that is executable, that will do things in the container right before training actually starts. I kept it simple. I just made that TensorFlow file executable and called it training, called it train. Okay, so that's what's in the repo. And remember, when I committed, that's what caused Code Pipeline to wake up and start the first stage. So it's going to take the contents of that repo and push it into an S3 bucket. So let's go ahead and let's take a look at that now. So what I have here is the AWS console, and we're going to click into Code Pipeline. And what you'll see on the screen are several pipelines, but we'll see the pipeline of interest that was instantiated when I ran that small little utility that I created, right? And this was instantiated via CloudFormation. And what you see here are my 3 stages. The first one, the source stage, it's already completed. It's that fast. The second stage, the build stage, is currently in progress. And the last one, the train stage, hasn't yet started. So we'll go up to the source stage, and let's take a look at that. So this is Code Commit, and you can see here the contents of that repo, right? So I have here all my files and my model. If we go into the commit, you'll see here all of the changes. Everything's green because this is my initial commit. So you can see my build spec file, my actual model. And what I'm going to do now is I'm just going to copy the commit ID and just put that in my clipboard buffer. So at this point, at the end of this stage, we have all of that stuff in an S3 bucket that the rest of the pipeline can now refer to. And now we go to the second stage. This is the build stage. And remember, this is where that Docker container is constructed and it's pushed into ECR. And what we have at the end of this is a container that's got all of that information that we're going to need later to be able to answer those questions, to be able to support this workload. Let's take a look at that now. So we go back to the pipeline, and with just we see here now that the build itself has started. We're going to click into this build, and we start to get details around how code build actually functions and what it's doing. And what you'll see here is I've configured code build to look for the build spec.yaml file in the root directory. And if you look down here, you'll see the build logs. And this build log here is all of the output that's associated with everything that I've configured code build to do on my behalf. So if we start to tail those logs, you'll see the output that's associated with the pre-build phase, logging into ECR. You'll see that I'll start to construct the Docker container by pulling down that TensorFlow GPU container. And then what I'll start to do is copy the contents of the repo into that container. And then you start to see all of the libraries actually be installed in that container. And once that's done, that's now pushed into ECR after all of that metadata has been pushed in. So that's the conclusion of the build step, and now we go to the last stage. This is where Code Pipeline now wakes up the Lambda function. And what that Lambda function is going to do is, of course, create that API call. It's going to refer to the container image. It's going to refer to the inputs in the bucket. And that's going to result in a training job, which will ultimately result in output into the output bucket. Let's take a look at that last stage now. So we're back at the pipeline, and with a quick refresh of the browser, you'll see that the build stage is now completed, and now we start with the train stage. So if we click into the training stage, what we'll see here is we'll see our Lambda function. So we'll do that now. And that Lambda function, remember, has been configured to just do one thing, and that's to construct the SageMaker API call. So we have our Lambda function here on the screen. It has a very specific set of permissions as to what it can and cannot do. And I have here code that what it does is it tries to send to training. And it tries to do that by calling the SageMaker service and calling the specific API call called create training job. And all of those variables, all of that information, it's able to pull from that manifest file that is in the source code root directory. So the machine learning professional has all of the control to be able to say how they want their job trained and what the hyperparameters are, et cetera. So at this point, that Lambda function has done its job, and now we actually go into SageMaker itself. And what you see here in SageMaker is the list of my training jobs. And you see here that we have it in progress. So now, if we click into that training job, you'll start to see some of the metadata associated with this particular job. Things like its creation date, its modified time. You'll see what algorithm it's training, what training image is supporting it, and what container is supporting it. And if I just search for the commit ID that was in my buffer, you'll see here it's the same Docker container that we've been using throughout this process. You see here information around what instance type is being used for this training job, and then also information around what input bucket, what output bucket is being used, and then all of that hyperparameter information. And then as we scroll all the way down, we'll actually see our tags. And this is where we have the SageMaker job actually tagged with information around not just the commit that woke it up and caused this training to happen, but also what is the version of the inputs that were used to train this particular model. What I do now is I just go back to the pipeline, and you'll see here all of the stages are now completed, and the solution is done, right? So at the conclusion, when this particular training job is done, it's going to output into that S3 bucket. So What's nice about all of this, of course, is that all of the orchestration is being handled by a machine, by a service, that makes certain that all of this stuff happens over and over again in the exact same way. So let's just pretend for the moment that we're going to go 6 months into the future, and myself at my pretend marketplace lender job that I've always wanted to work at since I was a young lad, we're going to go ahead and do a sample audit. I'm going to have a colleague show up, and I've got here this marketplace lending organization I've set up, and as you can imagine, I have a small little app that I've put onto smartphones, and I've got a customer, and that customer wants to apply for a loan. Now, as you can imagine, my make pretend system here, it has several subsystems, things that take care of providing information about products or running the website, but there's the subsystem of interest here, and that's our actual training model, right? The places where we decide whether or not to actually make this loan. So what we've configured here is a SageMaker endpoint that stands in front of our trained model. And what this allows us to do is to send data in that the model can then use to create an inference. And what I've done is I've configured this so that every time a request comes in, I copy the request, I create a new inference ID, and I take the inference itself and I write that into a table. That data is what's going to give me the initial string I need to pull to get all of the information that would allow me to answer an audit if it were required for this particular workload. So my colleague shows up and he says, hey, Felix, I've got this inference ID. We made a loan, and I would like information about all of the infrastructure that was involved with doing this thing. Now, if I had that typical workflow that I showed you a little bit earlier, my palms would be a bit more sweaty, but I know that I'm in a good place. So I can answer questions like, what was the version of the model that produced this inference? And who made the latest change? And also, what was the version of the training data that this particular model was exposed to? And I can do all of this because of the particular solution that I've been using. So remember, I have that nifty little utility. It's got a second piece of functionality, and that is it allows me to audit projects. So what I'm able to do here is I'm going to take that inference ID that's been given to me, and I'm going to pass it to this utility, and I'm going to hit enter. And when I do that, I'm going to make a database call, and that's going to return back a little bit of information that I now need to pull back all of the information required to be able to answer this audit. So if you look here, I now know what was the endpoint that produced this particular inference, how was that thing configured, what is the model that this endpoint is fronting, what is the container that makes up this model, and then I can pull out the container ID, I can look at its others tags and say, okay, now I've got the name of the repo, and with that information, I can send an API call to Code Commit, and now I can answer things like, it was Felix, he did it at this date, at this time, and with a quick call to SageMaker, I can also answer, this is the version of the training and testing data set that was used. And I can use that to go pull that object from those S3 buckets. All of this information is way easy to get, and that's in part because of all of the work that we did to make sure that everything was tightly linked together, and also because it's all AWS services. So with one database call and 5 API calls across 2 services, I was able to pull all of that information very, very easily. And that's exactly why my customers who have workloads that require significant rigor, given the space that they work in, particularly like this solution. So I hope you'll agree that the solution itself, it's pretty flexible, right? We can take any model. We can give the machine learning professional direct control over the runtime environment. It's collaborative, right? It's all Git-based, so you're not really changing much of their experience, especially if they're doing that today. It's repeatable, so you can instantiate this solution over and over again, and you can run the same solution over and over again by just making the commits, and it will behave exactly in the same way. It's pretty auditable, and of course, it's fairly secure. So I hope that you guys, having seen this solution, that you can, in some ways, either incorporate it in whole or take parts of it that may be useful to you. So if you're interested in more stuff around this, there are sessions tomorrow that you can take advantage of that will go into, for example, SageMaker itself a bit more deeply, and will go into the training process more deeply than I have here today. And with that, I'd just like to thank you for your time. Really appreciate it, and if you've got any feedback, send it. Thanks, everyone.